Hello all. In today's lecture, we will be showing the demonstration of recurrent neural networks, in short called as RNN, in natural language processing. Natural language processing is a domain of artificial intelligence which deals with text data. So, therefore, in today's presentation, we will be showing the demo of RNN on text data, that is Shakespeare text data. So, Shakespeare text data contains some poems, plays, characters and their dialogues. So, we will be showing how a next word can be predicted using the previous words, or the next word is predicted using set of sequences given initially. So, the objective is to understand how a recurrent neural network can be used to predict the next word in a sentence based on the previous set of words. So, we have already seen the working of recurrent neural networks in our previous lecture. So, directly I will go with the program code. So, first thing is importing the necessary libraries. So, libraries required are NumPy and most of the components required from TensorFlow and Keras. So, NumPy is required in order to deal with numbers, numerical operations or arrays. TensorFlow is required because we are dealing with the recurrent neural networks which is a neural network or nothing but a deep learning model. And from TensorFlow Keras pre-processing module, we import Tokenizer. So, Tokenizer is required in case of text processing because any text that we consider or a text data when we consider, it can have a group of paragraphs, it can have many number of paragraphs. Those paragraphs can be segmented into different sentences, and in a sentence there could be n number of words or n number of characters. So, we refer to those words or characters in a sentence or in a line in a data set as tokens. So, therefore, in order to perform tokenization, we need the function called as tokenizer. Then from the pre-processing module of TensorFlow Keras, we need something like padding the sequences. So, padding sequences means padding of zeros either before the input sequence or after the input sequence in order to make the sequence input sequence length uniform throughout. So, if you consider one particular line, the first line in a paragraph, it could have 10 words, maybe the second line could have some 15 words. Since we have to make those sentences or a line of equal length, we need to pad the sequences. So, we will see gradually in the demo, either we are going to do pre-padding or the post padding. Then coming to sequential function, it is required to stack the layers linearly. Coming to embedding, simple RNN and dense layer. So, embedding is required in order to convert the words into numbers or representation of the tokens or characters into vector. So, that is why this embedding layer is required. Then simple RNN is required in order to predict the next word based on the previous inputs or the previous set of words. And of course, the dense layer which is a fully connected output layer. And coming to matplotlib, that is required in order to have the 2D plotting. So, in short we call it as PLT. Next, coming to loading the data set. So, as mentioned earlier, we are making use of the Shakespeare text data set which contains several poems. So, the initial portion of this data set contains poems, that is why we will see a lot of words are repeating because they are rhyming and they are repeating. So, from TensorFlow Keras, we make use of the utility function and get the file called as Shakespeare text file, and then open this particular path in which we have stored the data set, read it and convert all the characters or all the words present in the data set into lowercase. So, the benefit of having the lowercase, all the representation in case of lowercase is so that we can have one uniform code word representation for it. So, for example, I take the word king in this poem. So, king, if it is in the beginning of the sentence, we will always try to have a capital letter, and then somewhere it comes in between of a sentence, but both the king words, they mean the same. So, instead of having a different representation for this king and this, because it is always case sensitive, right, Python is case sensitive. So, instead of wasting that representation, so this k is also converted into small letter. So, that this king as the king which is already mentioned in lowercase, they have the same representation. So, we know that model understands only numbers. So, these words or tokens will be converted into some numbers. So, if I assume the representation as 5, this will also be 5. In case we do not convert into lower case letter, then this should be given a different representation. Say if this is 5, this could be 6. So, now when I am mentioning about the representation of words or tokens in form of numbers, what we should understand is every word or every character or every token in the text will be converted into numbers. Now, on what basis these numbers are assigned is the frequency of occurrence. Say suppose the word king has appeared many a number of times in the corpus or in the text data, then that will be having a smaller number when compared to the one which is not frequent data. So, king has appeared twice, so we may represent it as 5. Suppose the word the has appeared many a number of times, obvious, right. So, the word the and will appear many number of times. So, then the keyword the representation would be something like 1 or 2, which will be definitely less than the king. So, the smallest representation, smallest number representation is given for those numbers which are very frequent in occurrence. So, that is about the importance of converting into lowercase letter. So, since this corpus or the data set what we have taken consists of about 1 MB size having 22 lakh characters, it is difficult to compute those characters. So, therefore, we are taking only 2 lakh characters for the program. In the program, we are considering only 2 lakh characters. So, that is saved in a variable called as text. So, this is the final data what we have, that is a text. Now, coming to tokenization. So, tokenizer will convert all the sentences or lines present in the text data into different words or characters. So, tokenizer is a function which is doing that. So, we are saving this tokenizer in a variable called as tokenizer, and this tokenizer is fit on the text data. So, our text is present in a variable called as text. So, it is fitting on this data. Now, what is the total number of words that we get after tokenization? That is exactly what tokenizer we have, the word index what is given to it. Suppose there are 500 different words, then we have the word index as 500 plus 1. This plus 1 is required always because we need to predict the next word based on the previous word. So, at least we should keep one word index extra so that we can predict always the next word. So, length of the tokenizer word index plus 1, that is going to give me total number of words. So, token list would be different, token list would be one value lesser than the total number of words. So, in our case we can say the number of tokens which are available in this text data is 4899 plus 1 is giving us total number of words as 4900. Now, when we say we have these many words, we have to create the input data to be given to the RNN model. So, we need to create sequences. So, for that we are making use of this code cell. So, I simply create one empty list so that I can store all the input sequences. So, input sequences equal to an empty list. Now, how do I segment this? I already mentioned paragraph could be segmented as sentences, and sentences can be converted into words. So, instead of just taking sentence by sentence, what we have done is every line in a if you consider a paragraph, every line is been split. So, for every line in the text data, we have to split it. Every line has to be split, and that is why we have this slash n. So, that the representation slash n is for a new line. So, whenever a new line appears, whenever a slash n appears, it is a new line. So, this tokenizer is applied and this text is converted into sequences starting from the 0th index, starting from the first line, we call it as a first line. So, for every integer I in the range 1 comma length of the token list. So, I already mentioned token list, the length would be 4899. So, starting from 1 up to the last token list, we have to consider all integers and prepare the input sequence. So, let us see how the input sequences look like. So, we take with the first word and we see what comes after the first word. We take the first two words and see what comes after those two words, nothing but the third word. Similarly, we take 1, 2 and 3, the word first three words, and see what comes as the fourth word. So, this is nothing but the input sequences that we create. So, as mentioned earlier, tokenization, it will convert into numbers also. Words are represented as numbers. So, we can see here the number representation is 39, 82, then we have 113, 25, 113, 25, 557. So, these are different words. So, if I am taking an example, of a simple poem which is present in this corpus, Shakespeare corpus, if I consider "O Lord," these are two different tokens which could be represented as 39 and then 82. Then the next sentence or the next line, "You are my sunshine, everything." Say for example, this is the line present. Then the tokens present in this particular line are "you are my sunshine" is another token, this comma is another token, everything is the next token followed by exclamatory mark, this is another token. So, when we say token, it can include words, it can include characters as well as special symbols like comma, full stop, exclamatory mark, space and every other special character. So, totally in this sentence we will be able to see 1, 2, 3, 4, 5, 6 and 7. So, there are totally 7 tokens in this particular sentence. Okay. Now, if I take a different line, a second line, "Your presence is all around me, I feel it." Say suppose this is the second line. Then the number of tokens are "your presence is all 4th one, 5th, 6th, 7th, 8th, 9th, 10th, and let me put a full stop. So, there are totally 11 tokens in it. So, if I take different lines, we have different unequal number of tokens. So, 7 tokens in the second line, in the third line we see 11 tokens, and in the first line we are able to see say 2 tokens. They are of unequal length. So, what we have to do is we have to pad the sequences, we have to insert some zeros either in the beginning of a line or at the end of the line, so that we make it equal length. So, this is nothing but converting the input sequences to a supervised learning format. If you remember, in supervised learning format we will have a data set comprising different input features, say x1, x2, x3, x4, which is then we have y, which is the target variable. So, every row, if you consider every row, we have certain values, and making use of these values we are predicting the label. So, the number of features using which we are predicting the label, that would be same. So, same way all these 2 tokens, 7 tokens or 11 tokens are to be converted into one particular standard token. So, if the maximum length in every line that you consider is say 11, after this also say 100 lines will come across and the maximum number of tokens in any line is 11, then rest of the tokens will also have to be converted into 11 different tokens by padding zeros. So, we have to pad zeros before this "Oh Lord," we have to pad zeros before this "You are my sunshine" and everything. So, we have to pad the zeros. So, now making the input sequences ready by converting the words, every word or character present into numbers. So, we see that 3982, that is the first representation. We are having 2 different tokens here, then comes two tokens, then we have 113, 25 and 557. This is the same line, but making use of 2 words in order to predict the third word, making use of 3 words in order to predict the 4th word. So, we are making the training sequences ready. These input sequences are nothing but the training sequences. So, we as mentioned earlier, since this is a poem, we can see that the same tokens are repeating, the same words are repeating. That is why we are able to see the same code word here. So, this is a set of training sequences we have in the data set. So, these are the sequences. As we can see, the number of tokens are different here. So, we have to make this of equal length. So, this is where the padding and labeling comes into picture. So, let me take the maximum length as maximum length of the sequence. We have already created the sequence. So, let me find out what is the maximum length here and convert all the tokens into the same length, or convert all the input sequences into same length. So, let me consider the length of the sequence for all the sequences present in my input sequences. Let me pad the sequences based on input sequences what I have, and based on the maximum length let me use the pre-padding. So that I have the representation 0 0 followed by the token values. So, finally, I try to print the total number of input sequences that I have and the maximum length of the input sequences. So, total number of input sequences that we have generated are 29,966, and what is the maximum length? It is 13. So, nothing but we are making use of 13 different features, or we are able to get 13 different features here, out of which the last feature what we have, that is our output. So, converting it into a supervised learning format in order to make the data ready for model building. This is the task performed in this code shell. So, we are able to see the padding done because we are able to see the zeros here, followed by the respective tokens. Now, once the input sequence is ready of the same size, of the same number of columns, we divide it into x and y. So, as mentioned earlier, we have input sequence length as 13, out of which 12 are the input columns, 1 is the target variable. So, in the input sequence I consider all the rows, and in the columns I try to avoid the last column, that is why I write it as -1 here. So, -1 indicates we are not able to, we should not be considering this last column, because that is our output which needs to be predicted based on the inputs given here. So, what is y? Out of the input sequences, all the rows I consider along with the last column only. So, here what numbers I find from the utilities function of Keras, TensorFlow, I convert into categorical. Why I say categorical is this is more or less like a supervised learning format now. So, we can consider it as a multi-class classification because the number of words are 4,900 here. We consider this as a multi-class classification. So, number of classes will be same as the total number of words, 4,900 different words. So, now I try to print the shape of x and y and the total number of sequences present. So, total sequences present are 29,966. Vocabulary size is nothing but the total number of words present in my corpus, so which is 4,900. Now, we see this x and y shape. We have these many sequences and 12 columns. We have these same number of sequences in y, but 4,900 different columns. Nothing but those many classes we have in the data set. So, once we are ready with the number of input features x and y, we are giving this data set to the model. So, we build and train the RNN model. So, RNN here, since we are dealing with the text data, there is one extra layer to be added, which is the embedding layer. Apart from that, rest of the layers would remain the same because we have to stack the layers linearly. So, we need the sequential, we need the simple RNN, and we are considering 128 neurons here, which is the dense layer neurons. In the embedding layer, we need to consider the total number of words, which is 4,900. We create a dense vector of length 100 and input is maximum length minus 1, because maximum length we had 13, 13 minus 1, 12 number of input features are the input length to be given to the embedding layer. And then we have the dense layer with the total words as the output. So, total number of words are 4,900 and the activation function what we are using is the softmax, because we are dealing with a multi-class classification problem. So, it is obvious that we have to go with the softmax activation function. And then compiling, model compiling. Let me make use of the categorical cross entropy. We cannot go for binary cross entropy because it is no more a binary classification. So, what holds good in a neural network for a multi-class classification problem is categorical cross entropy. And since I am making use of the adaptive learning rate, I am making use of this optimizer called as ADAM and classification problem. So, let the metrics be accuracy. So, I want the history of the losses and accuracies that I measure. So, model fit on x and y, let the number of epochs be 50, batch size be 128, and then the train test split, the validation split as 10%. So, 90% of my data is going for training and validation is only 10%. So, now coming to this epochs, number of epochs here, accuracy is going on increasing and loss is reducing as the number of epochs increase. So, that can be seen here. So, we are measuring the training accuracy, training loss, validation accuracy as well as validation loss. So, that we can have a nice plot of all these 4 metrics. So, accuracy is increasing whereas loss is decreasing as we progress through the epochs. So, coming to the loss and the accuracy plot. So, figure is the function which I am using, figure size is 10,6. So, 10 inches in width and 6 inches in height. I want to plot the loss, training loss, validation loss, training accuracy and validation accuracy. So, corresponding labels are also given, so that we have a legend for the different colors, and the title of the graph is training loss and accuracy. X label, let the name given to the X label be epochs and Y label as values. Let me show the legend here and then show the plot. So, we can see the training loss in blue color which is reducing, but the validation loss is little higher because I already mentioned the corpus size was having 22 lakh characters, out of which we have chosen only 2 lakh characters, so that we can reduce the computation time. So, that is why since it does not have a complete data set, we see that the loss is little bit high when compared to the training also. Similarly, the accuracy is increasing here, but in case of loss we have a little problem. So, we have seen how the loss and the accuracy varies in terms of training and the test phase. Now, what we try to do is, instead of having 128 neurons, we have already seen in the embedding layer we have 128 different neurons. We have seen it, we have 128 different neurons, but it is not, we will not be able to picturize or visualize how exactly the classification takes place or how exactly the next word is being predicted. So, what we try to do is, using the principal component analysis, we try to perform the dimensionality reduction. We reduce this 128 neurons into just 2 principal components, and we will try to visualize using only 2 axes, that is x and y, which are the words which are more near, that is more similar, and how it can be plotted. So, word embedding PCA visualization. So, what we try to do is, from scikit-learn I take the decomposition submodule, I am importing the principal component analysis which is used for reducing the dimensions present in the data set. I try to extract the embedding. So, I start from layer number 0 only, get all the weights. So, these are the embedding layer weights which are extracted, and using the PCA function I try to take only the first 2 principal components. Using only first 2 eigenvalues or eigenvectors, I am trying to get the most frequent words or the most important words which are required for the prediction. And then I try to fit this PCA onto the embeddings, plot the first 100 words which could be predicted. So, again once again drawing the figure for every integer and the word in the tokenizer word index keys, I try to take only the first 100 words. So, what are my new x and y? Those are only the first 100 words. So, nothing but what is saved under my embeddings 2D. I want only 2-dimensional figure, that is why I call it as embeddings 2D. So, let me have a scatter plot of x new and y new, and let the text appear on x new and y new at a difference of 0.01. So, that can be seen here. Suppose we have the scatter, we have some values in the x axis, we have some value on the y axis which is nearly equal to 0.5. So, the scatter is here at a difference of 0.01 on the x and on the y, we have this text representation, because we should be able to see what is the scatter all about, what is that word all about. So, we try to write the text on that x and y points. Let the font size be equal to 9. So, the title of the graph is word embedding or PCA visualization. I try to show the graph. So, we can see in the graph that the similar words, they try to scatter around the same set of words. So, suppose we see this communious, this is a very outlier or very rarely used word, very less frequent word, that is why it acts like an outlier. Whereas, we see the words he and his pronouns which are similar, which are belonging to a male category, and that is why they are nearer to each other. And if we see here, we have people, we have citizens. So, these are the same set of words like people, population, citizen, they refer to the same similar words, that is why they are together. So, the uncommon words, they are very far in the corpus. So, now coming to the last part, next word prediction function. So, how do we write this next word prediction function? We have seen how it is able to classify the next word, but how exactly it works in a sentence. We will take one example and see what exactly comes after the first few words or first few tokens. So, we define this predict next word. This is a function which is written on the seed text. So, seed text is nothing but the input text what I am going to give. So, this is a noble of the after this I want to predict the next 5 words, that is why I am writing this as n words equal to 5. So, result would be seed text followed by whatever prediction comes later on. So, for some integer or from dash in the range n words, you can write it as some integer j or I in order to avoid the confusion, because we have already made use of the integer I earlier. So, I just wrote it as a underscore here. In the range n words, total number of words is 5. I want to tokenize the given sentence and convert into sequence. I take only the 0th sentence, that is the first sentence here. I pad the sequences, I take the maximum length -1, so that I should be able to predict the next word, always the length is -1, and I try to do pre-padding also. So, predict on the input sequence given. Here verbose is equal to 0, because after every word I do not want to display what is the next word. So, this is a noble of the, then you would get one word, then the next word. So, I do not want to display that, that is why in simple I have kept it as verbose equal to 0. So, now I want to see the argument for all the maximum prediction probability. So, every word will be assigned some prediction probability. What is the probability of that occurrence of this word, say as, after this the word? What is the probability of occurrence of the word is after this the? So, every token will be assigned some probability. So, what are the maximum probability? What is the argument for the maximum probability? Only those to be displayed. So, for every word and index in the tokenizer word index items, if index is equal to what is prediction, what is the prediction done by the model, that result would be added to the word. So, whatever result, it is to be added to the previous words or the tokens, and then return the result. So, what is the test prediction? We have taken a simple seed sentence as this is a noble of the. We are trying to predict the next word, the seed followed by the 5 words. So, this is a noble of the 5 words which are being predicted based on the probability are was and safely home was. This is the prediction. So, likewise, if we try to get the higher probability words, what are the probable words which may occur after this sentence? That is what can be seen here. So, the word was can appear with a very high probability, say nearly equal to 0.45. The word town may occur soon after that sentence with a probability of 0.12. The word gods may occur with a probability of 0.05. So, this is the probability of occurrence of several words, say 10 words after this sentence. So, again the same procedure is being followed. Tokenizer converting the words into sequences, nothing but words. I take only the first sentence or nothing but the 0th index sentence, pad the sequence using pre-padding, and maximum length is maximum length -1, because we have to always predict the next word, and predict it on the sequence. I do not want to display what is predicted after every word has been captured. So, I keep the verbose equal to 0. I want to have the prediction probability for the 10 different words which are coming, and I want to display all the prediction probability, have the graph of top words with the probabilities. The title would be next word probability distribution for the seed sentence, this is a noble of thee. On the y label, as a y label, I want the probability. So, this is how the graph appears. So, in this lecture we have seen the demonstration of recurrent neural networks and prediction of the next word. So, this is one of the applications in natural language processing. Thank you.